Alright, well, welcome back. This is section 4.3, Irreducible and Unique Factorization. Alright, so a reminder. In a ring with identity R, an element A in R is an associate of an element B in R if there exists a unit U element of R such that A is equal to B times U. Remember, unit is a multiplicatively invertible element, so A and B are associates if there exists this multiplicative invertible element U such that A equals B times U. There exists an invertible element U, a unit, such that when I multiply it times one element, I get the other element. So, in a polynomial ring, where we have f adjoined x, where f represents a field, so my coefficients are coming from fields, then f of x, little f of x, is an element of f adjoined x, is an associate of g of x, element of f adjoined x, if and only if f of x is equal to a constant times g of x for some non-zero constant c that's an element of f, the field itself. Why? Because the only units in f adjoined x as a polynomial ring are the non-zero constants c and f. And these guys, you can also look at them as functions. So h of x equals a constant. And remember, a constant graph is a horizontal line if you try to think about graphing these guys or whatever. But it actually is a function. And it's a polynomial of degree 0. So an associate, two polynomials are associates if they're pretty much equal to each other with a constant being pulled out front. So f of x is equal to a constant times g of x. So the only difference between the two is this idea of multiplying by a constant. We're going to call these guys associates. So, what the big idea in chapter 4.3 is this concept of irreducibility. Definition. Let f be a field. A non-zero polynomial p of x, element of f adjoined x, is said to be irreducible if its only divisors are its associates and the non-zero constant polynomial's unit. A non-constant polynomial that is not irreducible is said to be reducible. Alright, let's talk about English here. What exactly is irreducible? An irreducible polynomial in English is a polynomial that can't be factored. So, but everybody can be factored. That's right in terms of pulling out a constant. We don't care about pulling out of constants. I know way back in high school, if you had polynomial 2x squared plus 4 and you factored out the 2 and you got 2 times x squared plus 2, you thought you did something or other. Not in this world. Pulling out constants is not considered to be reducing the polynomial. A constant is the only elements that are units, and the non-zero constants that are, and therefore pulling out a constant, that makes the two polynomials associates. So in terms of that idea of associates, like I said, if I let f of x be equal to 2x squared plus 4, and then I can factor out the 2 out of the thing, and I end up getting x squared plus 2. Now then, f of x is equal to 2x squared plus 4, and g of x is equal to x squared plus 2. Now they're not the same polynomial, f of x and g of x, but they're what we call associates. These guys are associates of one another. The only difference is I had to multiply this one by 2 to get this one. And 2, in the world of the fields, that has a multiplicative inverse of 1/2. That also is an element of your field. So the non-zero constants are the unit guys. So you multiply this one by a unit to get this guy over here, and therefore 2x squared plus 4 and x squared plus 2 are associate polynomials. So that's not considered doing anything. So to be irreducible, you got to knock him down by it. So an irreducible polynomial is a polynomial that can only be factored by pulling out constants, and that's it. Okay, it's only divised as are its associates, and like I said, the non-zero constant polynomials, pulling out constants. Okay, so this is the main idea, that this is considered to be irreducible if you only can factor out as the constants. But if you can actually bring out more than just a constant, we're going to call that reducible. So, Theorem 4.11 says this. Let f be a field. A non-zero polynomial f of x is reducible in f adjoint x if and only if f of x can be written as a product of two polynomials of lower degree. So what we're talking about here, this is your idea. F of x is equal to g of x times h of x. You can factor this thing, where g of x times h of x, where the degree of f of x is greater than the degree of g of x, and the degree of f of x is greater than the degree of h of x. So these guys have to be smaller degrees. That's how you factor something or other. You have to factor in terms of smaller degrees, and that makes f of x actually reducible. So if you can't break them into smaller degrees, it's irreducible. So we're kind of breaking this stuff up. So take a look at your next theorem, and then again, the key to math is catch a pattern. So Theorem 4.12. This is kind of a big theorem, so let's take a look at it. Theorem 4.12 says this. Let f be a field, and p of x a non-constant polynomial in f adjoint x. Then the following are equivalent. Now, we're math majors in here, or math minors, or something here. Mathematicians are inherently lazy. So when you get into another professor's class of higher level, like the 3 and 4 and 5,000 level classes and 6,000 and 7,000 graduate school and stuff, you'll see professors in math write down TFAE. Why? Because they're lazy. TFAE stands for then the following are equivalent. The following are equivalent. TFAE. So just want to throw a little bit of math knowledge your way in terms of your future classes and the like. So the following are equivalent. P of x is an irreducible polynomial. P of x is irreducible. 1. 2. If b of x and c of x are polynomials in f adjoint x such that p of x divides b of x times c of x, then p of x divides b of x, or p of x divides c of x. So if you've got a polynomial that divides both b of x and c of x, then that forces there to be either p of x divides b of x or p of x divides c of x. That tells me that p of x had to be irreducible. And if it's irreducible and you've got a polynomial that divides a product, it's either got to divide the first guy or it's got to divide the second guy. Property number 3 says this. If r of x and s of x are any polynomials in f adjoint x, of course, such that p of x is equal to r of x times s of x, then s of x or r of x is a non-zero constant polynomial. So if you've got an irreducible polynomial and you have factored it, broke it down, r of x times s of x, if this was true irreducible, the only way you can do that is one of these two polynomials had to be the, quote, non-zero constants. We don't consider factoring out a constant actually reducing it any. It's just pulling out a constant. That's great, but that's not reducing it. So if you have this particular case that anytime I can factor a polynomial, one of the factors has to be a constant, then the polynomial is irreducible. Now, what's the pattern? The pattern, of course, is that this irreducibility, when you look at it, and you're right, we're calling it p of x for a reason, it is like a prime. Now, this is not a prime polynomial. We don't have a prime polynomial. We've got a name for it. It's prime-ish. A prime-ish polynomial is that irreducible polynomial. It has the same patterns as what prime integers did way back when in chapter 1. So this idea of prime and the idea of irreducibility is actually connected. They have the same idea. Now, we're in a different world. This is a completely different world. This is the world of polynomial rings, but the concept is the same. What do you think of when you think of a prime integer? It's an integer that can't be factored but by plus or minus 1 and plus or minus itself. Yeah, okay, so we extend that a little bit. So for an irreducible polynomial, the only way you can factor it is you can only factor it by a non-zero constant and another term which would actually have the exact same degree. You can't break it down by a degree. The degrees don't reduce, because if the degrees reduce, that actually makes it a reducible polynomial. So there's the main idea, and you'll notice that Theorem 4.12 is very much like it was worded in Chapter 1 with the properties of primes. So irreducible and prime are very similar, but when you deal with polynomials, you don't call them prime, you call them irreducible. Therefore, following along the same suit, we have this. Corollary 4.13 says this: let f be a field, and p of x an irreducible polynomial in f adjoint x. If p of x, and yep, I used the divide symbol. You don't get to use it, but I'm the professor, so I do. So it divides a1 of x times a2 of x times dot 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 times an of x. Then p of x divides at least one of the ai of x polynomials. Now, what's the big deal on that? Well, this is a corollary 4.13, so it must follow from Theorem 4.12. For Theorem 4.12 pretty much said this in that part 3. If p of x divides, a1 of x times a2 of x, the Theorem 4.12 says that p of x either has to divide a1 of x or p of x has to divide a2 of x. Well, what we're going to use in terms of this concept of proving that when p of x divides a string of products, it has to divide at least one of them. Basically, you use the concept of induction. So you break it into two polynomials. So you can look at the first polynomial, a1 times, put little parentheses around the rest of them, times the rest of them. So if p of x divides a product, it either has to divide the first guy or the second guy. If it doesn't divide the first guy, then it's got to divide the second guy. So p of x divides the second guy, and then you kind of run down the line. It either has to divide a2 of x or it has to divide the rest of them. If it doesn't divide a2 of x, then it's got to divide the rest of them. And you kind of march your way down the line. That's an induction proof. But the fact of the matter is, when you got an irreducible polynomial dividing a product of a bunch of polynomials, it's got to divide at least one of them. It may divide more than one, but at least one of them it's going to divide. Theorem 4.14 says this. Now, I restated Theorem 4.14 because it was a little more lengthy in terms of the unique factorization concept, but it's the unique factorization concept here. And it says this: any polynomial f of x, element of big F adjoint x, where big F is a field, is the product of irreducible polynomials, and this factorization is unique up to order. So if I've got a polynomial, I can factor this polynomial as a product of irreducible polynomials. Now remember, irreducible, you can always pull out a constant. We don't care about the constants. So this factorization is going to be unique up to, we don't really care about the constants you pull out, but we also up to order. Now if you've got, f of x equals g of x times h of x, then f of x also equals h of x times g of x, because f, being a field, adjoint x means the polynomial ring is actually an integral domain, which is a commutative ring with identity, but it's a commutative ring, so we don't care about the order that you guys. So that's what I'm talking about, up to order. You can put whatever order you want to, but p of x, g of x in the front, g of x in the back. We don't care about the order, but the factorization will be unique. So you can always factor these polynomials uniquely into a product of irreducible polynomials. Now, the big question is, how are we going to factor these particular polynomials? Now, we kind of hint around with it with your homework out of the textbook in section 4.3, but they're trying to give you guys a feel for this stuff. But the real deal is some stuff that we did way back when in high school Algebra 1 and Algebra 2. It's going to come back and haunt us. So for all my teachers out there that are taking this course, some of that stuff that we teach our high school kids in the 10th, 11th, 12th grade in terms of the remainder theorem and the factor theorems and the like. They're going to come back and haunt us. And we're going to have to rewrite them in the sense of polynomial rings, but it's the same exact things we actually teach our students in high school. So, how we find the factorization of a polynomial f of x and f adjoint x, where f is a field, will be our focus in section 4.4. So section 4.4 is actually going to be the meat of this stuff. So section 4.3 is all theory of the idea of an irreducible polynomial definition and it being a factorable prime-like polynomial. Irreducible, you can't factor it. Reducible, you can factor it. So how we're actually going to be factoring these polynomials and how to set that up is going to be our focus on 4.4. And if I do my job right, I'm going to remind you of the material that we discussed in high school, something called the remainder theorem and the factor theorem from high school is actually going to be how we do it. We're just going to have to rewrite it so we can use this f adjoint x notation stuff. So I'll see you guys on the next set of videos.